Okay, so this is WebWork 14, problem number 10. We're working on an initial value problem where the right side of the equation is a piecewise function. And the initial value of y0 is equal to 9. So, our first step is going to be rewriting this equation where the right side is in the form of a unit step function. Which will allow us to take the Laplace transform and solve the differential equation. So we'll leave the left as it is for now. And basically what we've got here is two values, 0 and 10. So 10 is the value of the equation when t is between 1 and 7. So I'm going to leave 10 outside of the unit step functions for now. Our first value that's going to take occurs at 1. So this is going to become a value of 1, which is going to give the right side of the equation 10, a value of 10 at 1. And to zero it out at 7, we'll just subtract, the unit step function at t minus 7. There we go. So now, step 2, we're going to do two things. We'll set up the Laplace transform and take the Laplace transform. I'll also distribute the 10 out into those two values there. So we have our Laplace transform of y prime plus the Laplace transform of 5y equals 10. It's a constant, so we can pull it out of the Laplace transform, times the Laplace transform of the t minus 1 step function minus another 10 there, Laplace transform of the unit step function t minus 7. Alright, so now we're going to solve these Laplace transforms. Laplace transform of y prime is s capital Y of s minus y of 0, which we know the value of. We'll enter in that value next, plus the Laplace transform of 5y, which is 5 capital Y of s. Alright, equals the Laplace transform of our unit step function is going to be our constant 10 times e to the negative as, where our a here is 1, so we'll just have a negative s over s. And subtract, again, our constant stays out front, e to the negative a, which is 7, so the negative 7s over s. Alright, so step 3. We're going to go ahead and solve for y of s, who's here, and we're also going to plug in 9 here in order to do it. Do two things here. I'll plug in 9, and I'm also going to pull the y of s out of here. We're going to end up with y of s times s plus 5. So y of s times s plus 5. Apologize if those look too similar. Alright, and then we're going to have our 9 here, so minus 9 equals our right side of the equation. So I'll go ahead and add 9 to both sides, and we're going to divide both sides by s plus 5. That's going to result in our isolated y of s equaling 10 e to the negative s over s times s plus 5 minus 10 e to the negative 7s over s times s plus 5 plus 9 over s plus 5. Alright, so our next step is going to be taking the inverse Laplace transform now that we've solved for y of s. Unfortunately, we're going to have to do some work here, specifically partial fraction decomposition, in order to do that. This term down here, or at the end, is fine. We can do that, but we'll save that till the end. So I'm going to give us some space here. And we're going to go ahead with step 4, which is our PFD. Alright, so we really only have to do this once because these terms are essentially identical. The difference is this e to the negative 7s and e to the negative s. Those are the unit step function components of these terms. So we're going to actually just leave these out front and do the partial diffraction composition of 10 over s times s plus 5. And then when we we'll redistribute the e to the negative s when we're doing our inverse Laplace transforms. So we'll start just by setting our partial up here, s plus 5 equals a over s plus b over s plus 5. So this is pretty straightforward. We're going to have 10 equaling a, I'm just going to distribute the a there, s plus 5a, and then we're going to have just bs plus bs. Alright, so setting up our like coefficients, we know that 10 is going to equal 5a, and we know that 0 is going to equal a plus b. So a equals 2, which if these are equal to 0, we know that b is equal to negative 2. So that's going to get us 2 over s and, minus 2 over s plus 5. And we can go ahead and plug these back in, remembering that we've got these e to the negative s and e to the negative 7s out front. So we're going to have y of s equals 2 over s minus 2 over s plus 5 times e to the negative s minus, repeat that, 2 over s minus 2 over s plus 5 times e to the negative 7s plus our last term, which doesn't change, 9 over s plus 5. All right. Give ourselves another bit of room here. Step 5. All right, so now we're going to take, let's clean this up a little bit, and then in step 6 we'll take the inverse Laplace transform and solve for y of s, or solve for y of t. So we could probably pull out a 2 as we distribute these e to the negative s's, or maybe we'll just leave it all in and take the Laplace transform. Maybe that's what we'll do. So let's take y of s equals 2 over s e to the negative s minus 2 over s plus 5 e to the negative s. We're going to have to distribute this negative sign, so remember to turn that into a positive. So minus 2 over s e to the negative 7s plus 2 over s plus 5 e to the negative 7s plus 9 over s plus 5. All right, let's clean this up. For step 6, which is going to be our final step, we're going to take the Laplace transform of this, the inverse Laplace transform of this entire thing. We could just leave the 2 out of this, but that's okay. I'm going to pull the 9 out of this one just to make this simpler. Okay. All right, so it's pretty straightforward from here, with the exception of one item, which I'll get to. So y of s, capital Y of s, we're going to flip that back down into the t domain here. We're going to start solving these. So 1 over s, the Laplace transform of 1 over s is just 1. So we'll just multiply that by 2. So we have 2 times the inverse Laplace transform of e to the negative s, which is just going to be our step function, pulling a back out of that, which we remember is 1. So times u t minus 1. All right, now our subtract. Here's where things we need to change a little bit because there's a shift going on here. So we do have a unit step function that's going to come out of this inverse Laplace transform, just like we did here. So because this is going to equal e to the negative 5t, that t value is going to have to be shifted in order to get this function to operate properly. So we have, again, 2 e to the negative 5, and it's going to be t minus 1 to shift it to the right. So we get this to appear correctly when we solve it. So anyways, our next step is going to be pretty much identical to this, only the unit step function is going to be shifted to 7 instead of 1. So 2u t minus 7 plus, again, we're going to have 2 e to the negative 5. This time we need to shift it right by 7 times our step function of t minus 7. And that leaves us with our last term, which is pretty straightforward. We've already solved it a bunch of times here, but there's no shift, obviously, in this case. So 9e to the negative 5t. All right, and we clean this up. I think the way the answer is set up in the WebWork, the 2 is pulled out, and maybe some other things, but generally speaking, this is your answer.